Okay, so we're going to get to that in just a second. Okay, so now let's go back and take a look at our hood. Now the hood's got its own, we have our own deal for the hood, right? Each one of these different hoods, depending on their design, have various factors that we have to deal with. Okay, so for instance, what is K for a hood? Well, let's take a look at this hood. This hood is a 12-inch flanged round duct end hood. Okay, and we can look that up, right? That's on chart, is it chart 11? Am I right about that? Chart 11 has a number of different charts, 11A, 11B, and so on and so forth. No, it's not chart 11, it's chart 12. Help me out here. Nope, it's not chart 12. Chart 13. I'll keep trying until I find it. Nope. Why am I having trouble with this? Which one is it? 11A. There you go. Okay. What did I say? Just 11? Before hood. Oh, here you go. Hood. There you go. Perfect. Okay, good. So let's find our hood. Now, there's many different kinds of hoods here. I brought in the ACGIH manual on industrial hoods, and with all the factors and so on and so forth. I meant to bring it up so you guys could thumb through it and take a look at it. It's sitting in my car right now. I'll make sure I bring it up with me the next time. So at any rate, let's hear. We have any number of kinds of hoods. We have grinding hoods. We have open face canopy hoods. We have slot hoods. We have grinding hoods. We have all hoods here. Turns out, in this particular case, we're talking about a round, not a bell, but a flanged round end duct hood. So for this duct, we know for this type of hood that the K value, the loss, the hood entry loss factor is 0.70. The coefficient of entry is 0.77. What is the coefficient of entry? Coefficient of entry is a measure of the ideal flow rate for this hood. The actual flow rate for the hood divided by the ideal flow rate for the hood. It's basically the efficiency of the hood, right? In terms of like what kind of losses you have. But we mostly not going to use that. We're mostly going to look at this K factor because it's a direct measure of the hood entry losses that we can use with the velocity pressure. Yes. I'm sorry. Did I move down? Yeah, I moved down. Spatially, I kind of lost track of where I was. Yeah, it's this one right here. Okay, so our K factor is 0.50, right? And our the formula that we're going to use for calculating the quantity of air that we need to achieve the capture velocity is given in one of these two formulas. I posted something last week in the class notes that I think I put an announcement up too, that these two formulas are derived differently. This one is derived theoretically using a kind of a mathematical construct. This one is derived based on experience or manufacturer's recommendations for that type of hood. Mostly experience, in the case of this simple hood, mostly on the basis of experience. So most people tend to use this second formula. Okay, so you can use either one, but most people tend to use the second one. So now what does it have in it? This gives us the quantity of air we have to move to achieve the capture velocity we want. Well, what is that based on? That's based on the capture velocity we want, the area of the hood. That's this hood face. Okay, the area. What is that? That's F for hood face. The area of the face of the hood, and the X, which is the distance in front of the hood that we're measuring the capture velocity. So let's go back to our problem. Let's see, K is equal to 0.5. Might as well put that down right now so we don't forget it. A coefficient of the entry, I'm not going to bother with that because we can just write that down later. I'm not going to use it as it happens here. And Q is equal to this formula. Okay, I'm going to see if I can't copy that formula and paste it into here. Okay. Oh, what do you know? Let me do it. Okay. And there's just a summary of what CE is equal to if you wanted to know it, if you wanted to happen to know it. Okay. So Q is equal to 0.75 times, okay, what are we going to put in there? 10 times the distance from the hood that we're measuring the capture velocity. Capture velocity at 200 feet per minute, 12 inches from the face of the hood. What are those units going to be for X? Going to be inches? Going to be feet, right? So I'm going to put 1 instead of 12 inches, right? Squared. 1 squared is 1, so I'm not going to bother with that. Plus the area of the face of the hood. It's a 12-inch diameter hood. That's the face of it. So 12 inches, the area that's represented by 12-inch diameter. We just did that before. I think it was 0.785. Oops. Uh-oh. I lost the connection there momentarily. Hopefully it's back. Hi, guys. Brittany, can you hear me there? Brittany's a slow typer. Hopefully we're still online. Did you notice a message come up behind me? No. I got a message that we temporarily lost the connection.
Yeah, whatever you're typing,
it's not going through? No. Am I otherwise, was I keeping up before?
Within the last 2 minutes.
Connection restored. It's back. Okay. Oh, okay. I got you guys. Oh, Grace, you're on also. Okay, you guys are back, right? We lost connection there for a little while. The web connection here at Hunter is going through. It's been good off and on, but today it's not so good. So we're back on. So as I was saying, I hope that I back up far enough. Q, the quantity of air that we need to achieve the capture velocity that we want at that certain distance from the hood. Q is equal to, and we got this from that chart 11. Q for this particular hood is equal to 0.75 times 10 times the distance from the hood that we're going to measure the capture velocity squared, plus the area of the face of the hood times the capture velocity. So it's 0.75 times 10 times the distance that we're going to be from the hood. Excuse me, the distance we're going to be from the hood, where we want a 200 foot per minute capture velocity, 12 inches from the face of the hood. Well, areas that we're always measuring areas in feet rather than in inches. So I converted that to 1 from 12 inches. X is 1. Squaring 1 is going to be 1 anyway, so it's going to stay the same. Plus the area to face of the hood is going to be, can you see this behind me now? Did it catch up? Okay, if I highlight it, you can see me highlight? Okay, good. Yeah, we're caught up. Okay, plus 0.785, that's the area for that's pi times 0.5 feet times 0.5 feet. Pi r squared converted into feet. So that's 0.75, the area is 0.75 square feet. I'm going to put those together, and I'm going to multiply that by the capture velocity I want. My capture velocity was 200 feet per minute. I'm going to use those units, feet per minute. Okay, and my answer is going to be, let's see, 0.75 times 10.785 times 200. Anybody working on that while I'm doing this? How much? 16, 18? Okay, good. Okay, and what's the units going to be there? It's Q. Going to be CFM, cubic feet per minute, right? Okay, so now, if we were to measure, that's how much air is moving through this duct. Now, as it happens, this hood itself is a duct. So the diameter of the duct is going to stay the same. So if I have 1,618 cubic feet per minute moving into this duct, and I measure it 4 to 6 duct diameters up from the hood, what's my velocity going to be for it that far up the hood? Anyone want to hazard to get what my velocity is going to be? Right, Q equals VA. right? So my velocity is going to be 1618, right, divided by the area, right, which is 0.785, which is equal to, how much does that come out to for my velocity? I'm just thumbing through here so I catch up on where I was. Okay, I got an opinion there? Okay, I'll do it myself if you guys are not going to help me. What was that? 2061? Okay, 2,061 feet per minute, right? That's my velocity. What's my velocity pressure equal to? Right, it's going to be equal to 2,061 over 4,005 squared, right? Same formula we use for everything else, right? Okay, which is going to be is equal to how much? 0.26. And what are the units there? Inches of water. Okay, inches of water. Okay, so now let's see. Now I got to calculate my. I'm gonna go past this for a second. I'm gonna look. What I really am interested in is what negative pressure I need in this hood in order to generate this flow of air that I need to achieve my capture velocity. So my static pressure, right, is going to be equal to. Remember we talked about the positive. We were talking about using the positive value for static pressure when we use this formula. It's kind of what you're doing there is what I was having you do intuitively about, oh, the negative pressure, the pressure has to be more negative here than it is here for the air to move that direction. Okay, but they're using positive value instead in the formula in the book. It's going to be equal to the velocity pressure plus whatever we're losing from the entry loss, the hood entry losses. Okay, so what's that equal to? That's equal to the velocity pressure plus some K times the velocity pressure. And what's our K? Our K is, for this specific hood, our K is what was it? 0.5? Okay. So it's going to be equal to 0.26 plus our velocity pressure of 0.26 times, excuse me, I got that wrong. K is 0.5 times 0.26, right? What's that equal to? 0.4? Okay, but that's the positive value of the hood pressure, the static pressure for the hood, right? Measured a little bit up here. What is it really, that static pressure? It's not really a positive number, right? It's really a negative number, right? We calculated the positive value, but we know that the hood static pressure has to be negative 0.4, right? Is what it really is. Yes.
Why are we doing 0.26 twice?
The velocity K times it's not. Oh, I'm sorry. Say it again.
So it's 0.26 plus 0.5 times 0.26.
Yeah, this is the hood entry loss.
Right. So isn't that the K times the velocity pressure times V?
K times the velocity pressure.
Where's the plus coming from?
Oh, the plus is coming from the fact that I'm adding. I need both. What do you think it should be negative? Right. This is the velocity pressure. This is the energy from the air moving. I'm not sure why you don't think it should be a positive number, because I need this is my static pressure. Positive value of my static pressure is equal to the velocity pressure.
I'm sorry.
Plus something I have.
Yeah, your final number is negative 0.4.
Yes.
That's fine. I got that. You know what
Okay.
I did? I just solved for HE first and then plug it in.
Oh, okay. I'm sorry. Yeah, I kind of skipped that step and did it down. This is HE right here. Yeah, the K times the velocity pressure is the head loss. Right? It's the hood loss rather. Right. I kind of just did that right here. This is the same thing. This would be 0.5 times 0.26, the velocity pressure. But think about it this way, that the static pressure, in order to generate that velocity is going to be 0.26, but you're going to lose some energy that you have to make up for. So it has to be an even greater static pressure, negative static pressure, than you would have anticipated. In other words, the loss happens. We're calculating it as if the loss is happening going this direction, going into the hood, where really the loss is occurring, from behind the hood to the front of the hood. That's where we're losing static pressure, right? It's a little confusing, but if you just if you try it a few times more, you'll get a feel for like how the static pressures change. Okay, so what are we missing now? One more thing I want to do before we go on to looking at this overall as a system, and that is just quickly talk about transport velocity. Now, when you hook up to a hood, right? When you hook up, in this case, the hood that we had here was itself a duct. So it's going to be automatically connected to, it's automatically 12-inch duct, right? But normally you have a choice. I'm going to buy this hood. I'm going to install this hood. What size duct do I want to put on the outside of this hood? What do I want to connect to this hood? Well, how are you going to determine what size duct you want to connect to that hood in order to achieve the transport velocity that you want? Well, for your particular hood, what your Q is going to be, what quantity of air you move, based on your based on what the capture velocity has to be. You calculated your Q for the hood. For this hood, I need 5,000 cubic feet per minute for this hood. But now I also want to make sure that if I size this for too big a duct, the velocity in the duct is going to be slow. So I may not have the transport velocity I want. If I size it for too small a duct, it increases your frictional losses. It also makes the air move so fast that you may have vibration problems, noise problems, and so on and so forth. So you want to size the ductwork to match your velocity, to match the quantity of air you need to move. Okay, so for instance, the local exhaust is required to have 1,000 cubic feet per minute to achieve the desired capture velocity. You figured that out just the way we did before. In order to avoid deposition that we connected hood, we need to have a transport velocity of 3,000 feet per minute in the connected hood. What size duct should we connect? So the design number of cubic feet per minute is 100 CFM, right? The transport velocity was how much? Was 3,000 feet per minute. And we want to figure out what the ideal duct size has to be. Okay, so let's see. How am I going to figure that out? I could do it by trial and error. That might be one conceivable way for me to figure this out, right? What do you think? What do you think might be a reasonable size? Anybody got an idea? It happens that there's a formula they give you in the book, right? Okay, so now let's see. The formula that they give you in the book is in that chart 12, that analysis that they use for the book. We could do this by trial and error. I could try 6-inch duct, 8-inch standard duct size, 6-inch duct, 8-inch duct, 12-inch duct, and so on and so forth. We know what Q is, so based on the area, a cross-sectional area of the ductwork, I can figure out what V is. What V would be to give me 1,000 CFM for each one of them. Happens that there is a formula that they use in the book to calculate this. It's just as legitimate to just use trial and error. Okay, 13.54, right, times, let's see, let's see. What's that? Is it on the top? Times, okay, there you go. I didn't realize I wrote it up there. Q design over the target velocity. Over the target velocity. Okay, so what's that going to be equal? It's going to be equal to 13.454 times, what's Q equal to? It's equal to 1,000 divided by the velocity, which is equal to 3,000. Okay, and what does that come out to? It comes out to 13.54 divided by 3. equals 4.51. Okay, so what size duct do we need? Well, I'm kind of in a little bit of a quandary here now, right? Okay, if I go to 5, I'm oversizing it. If I go to 4, I'm undersizing it. So now you got to make a decision. If I go to 5, I'm not going to achieve my transport velocity I want, right? But I'm so close. Now you got to make a decision. I wanted 3,000 feet per minute because it's a certain kind of particle that I want to remove. But relative to what it could be, it's a relatively small particle. So maybe I'll go to 5-inch duct because I'm just going to be a little under the 3,000 transport velocity, but it should be good enough for my application, right? However, if you have a material that you're trying to capture that even 3,000 feet per minute is marginal, you might say, I'm going to have to go to 4. I have no choice. I have to use smaller ductwork at a higher velocity. Okay, and you can actually now that you've done that, you can actually go back and now calculate what is a transport. It's a 4-inch duct, and you're moving 1,000 cubic feet per minute. What's the velocity you get in a 4-inch duct? And it's going to be like 3,500 or whatever, 3,800 or something like that. Well, what's the velocity you get in a 5-inch duct? And you might figure that's, remember, Q is equal to VA. You might find that that's 2,800 feet per minute. So you have to make kind of a judgment on that. But you have to analyze, in order to decide what size ductwork you need to know what your transport velocity is going to be and what quantity of air you're going to move through there. You know what quantity of air you're going to move through there because it's whatever you need to get that hood to work, right? Okay, so now that we've done that, let's go and take a look at a duct system. Here's a typical duct system. Okay, what do we got? We got a hood, we got some duct, we got an air cleaner, we got elbows, we got a fan, and then we got a discharge from the fan, which goes to a stack. This chart describes the changes in total pressure and static pressure. So what's happening here? If you look at this, notice that up until you get to the fan, what's happening to the static pressure as you go across? It looks like the static pressure is going down. It's getting more and more negative. As we've been calculating this, that's what we've been doing. We've been making the static pressure more and more negative to make up for losses. What's really happening is the static pressure is starting at -4 inches, but we have a loss in an elbow, so it winds up going to -3 inches. And we have a certain amount of ductwork and an air cleaner, and by the time we get past them, it's -2 inches. And by the time we get to the just before the hood, the static pressure for the hood entry is -1 inch. So what's happening here is that we are designing in enough static pressure towards the fan that will make up for each one of the losses. We're designing kind of in reverse. Make sense? That's why as you look at this and you consider, well, if I go across here, this is my loss. So what I have to do now is I have to have a higher negative static pressure on side towards the fan than I have away from the fan to make up for that loss. So remember, all of this is why are you doing all of this on the suction side of the fan? You're doing all of this to get that 1 inch at the hood. That's your objective. Get that 1 inch at the hood. If you've got a lot of ductwork connected to it, then that ductwork is going to, if you just have a fan that'll deliver 1 inch, you won't have 1 inch at the hood because you'll lose all that static pressure before you get to the hood, right? So that's why we're continually working with finding out what the loss is through each transition, through each section of ductwork, and figuring out what static pressure we need at that fan in order to have the static pressure that we need at the hood. One step at a time. We start at the hood, we do it for the ductwork, we do it for the air cleaner, we do it for and the air cleaner is going to have its own factor for pressure loss. We do it at it could be just a filter, for instance. We do it at the elbows, we do it at the transitions, we do it at the convergences, and so on and so forth, until we get to that fan. And then after probably after the midterm, we're going to sit down and we're going to design that fan. We're going to figure out what fan do I need to buy in order to achieve all this. But first, I have to design all this ductwork so that I know what I need in the way of a fan. Okay, so now here's another typical system. On this particular hood, we need 1.2 inches of static pressure. Static pressure hood has to be 1.2, negative 1.2 inches in order to get the capture velocity we want in that hood. So in order to achieve that, we go through a couple of elbows and a length of ductwork. Just before the air cleaner, it has to be 1.6 inch, negative 1.6 inches, because we have a loss of 0.4 inches between the hood and that air cleaner. The air cleaner introduces a static pressure loss of 1 inch. So now we need a static pressure on the other side of the hood of the air cleaner, which is negative 2.6 inches, so that we make up for that 1 inch loss. So we get 1.6 inches here, and we keep the 1.2 inches here. So we have another loss here as we have more. Maybe that's flex duct. So we have to make up for the loss in this flex duct. So just before the fan, we need a static pressure of negative 3 inches in order to have this system deliver that negative 1.2 inches at the hood. The whole reason we're doing all this is to get that static pressure at the hood that we need to get enough velocity in there to capture the particles that we want. On the discharge side, we got the same issue, a little bit less critical for us, but we'll figure this out once we get to the discharge side. Okay, so now here is a simple duct system. Okay, so here we go in the simple duct system. The simple duct system, we have a hood, we have some length of ductwork, we have a fan, right? Then we have a discharge side. So when you guys go home, if you want, you can fill this out. First of all, number one is indeterminate. That's actually the hood itself, right? We're not going to do anything with the hood itself because it's really not going to be something that is really easily measurable. I think we saw another example here where it said the static pressure in the hood is negative 0.02, but we're not going to be able to measure that effectively. We can only, that's why we're measuring just upstream from the hood, because it's a location where we can get a reliable reading on what the static pressure is and the status of that hood is. Okay, so we can fill all this out. So for instance, right here, just a static pressure hood, when we know the diameter is 62 inches, we know the velocity is 3580, we've been given that. We know the cross-sectional area because we know the diameter. We know the velocity pressure because we know the velocity. We know the total pressure, we've been given that, so we can figure out what the static pressure is at that point, right? So you know what the static pressure is at 0.2. Anybody doubt me on that? Right? Total pressure is equal to static pressure plus velocity pressure. You can fill in all these blanks. Nod? Yes? Oh, I see nodding. Yes, I see nodding. Good. Okay, now number three. Point number three. What happens point number three? Is the static pressure at point number three going to be a bigger negative number or a smaller negative number than 0.2? It's going to be a bigger negative number because he has got to go that direction, right? So we can figure this out. We got the area. We got all the static and other pressures, so we can figure out what the velocity is, right? In fact, it turns out that the static pressure here, well, we didn't calculate static pressure here, but you know you can because you can calculate velocity pressure. Let's say that, for instance, that's -1. I don't know what it is, but you're going to calculate it yourself. So this is -2.3. So now after the fan, we're dealing with positive static pressures. It's pushing out against the ductwork, right? So we know the diameter of the ductwork. We know the area of the ductwork. What about the velocity, right? Well, the velocity is, if they didn't change the size of the ductwork, looks like the ductwork's all the same. If they didn't change the size of the ductwork, the velocity is the same, right? The quantity of air that you're moving, Q, is the same. And the velocity is the same. Only thing that's going to change the velocity is if you change the size of the ductwork, right? Because otherwise, the air's moving through that same size ductwork. It can't stack up or be absent anywhere. So you should, I'm sorry.
Isn't it being pushed on the fan end though because it's positive?
Yeah, what's happening now is the velocity pressure. The velocity determines the velocity pressure. So all through this system, the velocity pressure is the same. It's all moving the same direction. It's all moving the same speed. The velocity pressure is never changing. What's the only thing that's changing? The static pressure and the total pressure, right? So static pressure and the total pressure are changing because as the static pressure changes, total pressure changes. And most of that change in total pressure is really due to losses. right? Because that's what's making up for that static pressure change. So at any rate, so that's how you're going to go through it. Static pressure is going to be a positive number. It's going to turn out to be a positive number. And then it's going to go through this ductwork to number 5. So is the static pressure going to be a bigger positive number at 4 or at 5? It's going to be a bigger positive number at 4 because the pressure has to be lower at 5 for the air to move that direction, the static pressure, right? You can imagine it, the pressure's forcing, the fan is forcing the air in, so all that energy that's causing that static pressure is high by the fan, but you're losing some of it as it gets up the stack, right? So it's going to be high, but you're going to be able to calculate this. So if we just look at the static pressures here, where we're looking at 2, it's probably like -1. Then at 3, it's -2.3. You can do the actual calculations. Right after the fan, it may be as high as at plus 2.0. And then it's down to a plus 1.0 after it goes through the losses through the stack. So now you could actually chart this. So how would you chart this now? It's static pressure starting out at, what did I say, -1, right? So the static pressure at 2 is -1. So I would put a line there. Can I do that here? No, I'm in Word document. I can't really do this. Okay, so -1, right? And from there, at 3, it's going to be -2.3. So the line's going to go down to the fan, right? Then after the fan, it's going to jump up to a +2. And then and then going through the stack, you're going to lose some of that positive pressure, and it's going to slip down to the static pressure, going to slip down to a +1. So you can actually chart out the static pressure, positive pressure, and the total static pressure, velocity pressure, and total pressure on this table. So take it home and give it a try. Just one other thing, just want to talk about quickly, because it's on the PowerPoint. You can actually go through the PowerPoint on your own, and the one that we have from Jeff. Three types of systems. One type is a plenum type. You guys have gone into garages and you've seen, like, when they work on your car in a garage, these big service centers, that they have like a 4 or 6 inch flex duct comes down from the ceiling, and they connect it to your exhaust pipe so they can work indoors, right? That's a hood. And the way that works is they use a big plenum. They use a big duct with a fan that keeps that duct under the same pressure, because all of those hoses are the same size. So they don't worry about, head losses and stuff like that, because their job is just keep that plenum under this level of suction, and each one of these hoses is going to connect it, and they're all going to be the same size duct and so on and so forth. You just connect them to the system. So it's a relatively simple design. It's called a plenum type exhaust system, right? That's mostly where you see them in vehicle maintenance systems. Okay, now another kind of system where you don't do a lot of planning is a system where you have a fan that may be oversized for your needs, right? And you have an air cleaner or a filter or something like that. But then you have several ducts connected to it. And those ducts, in order to get the capture velocity that you want, instead of designing the ductwork so that the ductwork is sized in a way that you make up for all of the losses exactly that you need to get the velocity you need, the capture velocity you need at the hood. What you do is you oversize the fan so you get more than enough suction that you need for all of your hoods, and then you balance them with a damper. They call it a blast gate in these systems. And if it were an air conditioning system like this, it would be a damper, which looks like a butterfly. And you would adjust that to adjust how much air was getting pulled in through that hood, and how much air is getting pulled in through this hood. Anybody ever have like air stones in a fish tank? And if you got more than one of them, if you open up one too much, the other one doesn't get any air, and you can adjust the valve so you can balance them. That's how these things work. They adjust the blast gates to achieve the velocity that they need in the hood. It's a kind of a real kind of inefficient way to do this, because you got to oversize your fan in order to make sure you have enough air going to all the various devices, and then you have to rebalance them every once in a while if anything changes. The kind of ductwork we want is the kind that's self-balancing. We don't have to worry that someone's going to come along, a monkey with these blast gates, and throw it out of balance. So this worker is getting a lot more air getting pulled away from him, and it's fine. But this guy's getting starved, so he's getting exposed to the material, and it's changed the balance in the operation of the system. We want a system that is self-balancing. That's what this is all about. We're calculating the duct sizes and lengths and so on and so forth, and the fan sizes. So this thing, as soon as this fan goes on, all of these hoods that are in here get exact the amount of air just by sizing the ductwork and the lengths of ductwork that we need to get them to balance for each other. Okay? So at any rate,